Yes. Okay. So, very good morning to all of you. This is the LEAP session 2 of this course Ironmaking and Steelmaking, and from the Google Drive I got only 2 questions. Okay. And one is basically how it is ascertained what is the correct time of tapping hot metal from the blast furnace, and second question is please explain various irregularities in blast furnace, their mechanism of arising and remedial action that should be taken to eliminate them. So, the questions 2 basically has been discussed in my lecture. If you go through the lectures, I think the lecture number I have to see that. I have just taken those lectures, I will just explain from that. But question 1 is very relevant, I have not discussed in my lecture, I will definitely address to that question. I do not know how many of you are present in this LEAP session. Last time it was around 100, and also I find that this time number of registration for the examination is also very less, 28. I do not know why. Anyway, so let us start. The first question, how it is ascertained what is the correct time of tapping of hot metal from the blast furnace. It is a very usual problem. Actually, this is the problem day to day we face, because it is not possible to continuously measure the hot metal composition. So, main thing is that how do you know the ascertain the what is the tapping time means when the temperature is required temperature and the carbon percentage is the desired carbon percentage and the desired temperature, what is the amount of the superheat you require, that is very important. So, you want to tap the liquid steel at a particular temperature and with a desired carbon percentage. So, if these 2 conditions you can predict, then only you can say this is the time for tapping. Okay. So, there has been different models. There have been several models, like you have analytical models, that is the based on phenomenological models are there, but there are several models based on artificial intelligence only. There is neural network or like that, regression analysis and all that thing, then predict. So, in that case basically stochastic model, basically you train the model with the previous data, okay, from the previous tapping operation and several tapping operation. If you train the say neural network, and then it can predict. Okay. And neural network has a capacity of both forward and backward prediction. So, it can do the inverse modeling also. That means, for a particular endpoint conditions, like what is the percentage of concentration of carbon and temperature, you can predict what would have been or what will be the operating parameters. So, for particular desired point, you know at a particular time what should be the operating parameter, that you can predict with this neural network has that capacity. But if you train the neural network with the data only, since the physics of the process is not involved in it, and if your input parameter changes, then it becomes a problem, because it becomes it learns from the system, from the previous data, and in the data lot of noises are there, not a lot of noise will be there, because the plant operation you know dynamically lot of problems occurs, like for example, one example, some slopping, sometimes if slopping is happening, your data will be different. If without slopping, with slopping, your data will be different. Those are the things are there. And raw material, suppose the hot metal composition can vary, but you may consider that is the you are taking the source is same, you may consider that it will not vary, but it is like it can vary definitely hot metal composition because of depending on the tapping temperature, the silicon percentage from the blast furnace obviously varies. So, this hot metal composition can vary, and then your what is that your proportion, that is the scrap proportion can vary depending on the situation. Okay, so and also if you are adding DRI also a lot of things. So, input material, if you change the input material also, and suddenly the neural network won't be able to capture it. So, and other noises because of irregularities into the operations, a lot of noises can generate. So, that also can be done, but it is always better to involve some phenomenological model, that is model based on the physics of the process. Okay. And if you train those, and if you train the neural network using some phenomenological models, then the neural network prediction will be much more better, is based on the physics. So, you can train the your model developed based on the physics. If you develop the model based on physics and train neural network with that model, and then if you predict it, because neural network has the both prediction capability, it can predict in the backward mode also, that is called the inverse modeling, and we need the inverse modeling. Basically, we want for a particular desired composition of carbon and temperature at the end point, what will be my operating parameters. If the neural network is properly trained with the phenomenological model, then it will behave like a phenomenological model, and then it can predict your input parameters, right, or the operating parameters at a particular state of time. So, this is the thing. So, I always prefer, that is you work with the phenomenological model and then couple it with the neural network, and then that thing. Now, phenomenological model, basically what I mean, you develop the model based on heat and material balance and equilibrium, and also the condition, that is the heat and material balance, and you can assume that is the reaction. Most of the cases, a model I am going to present where it is assumed that reactions are at equilibrium, all the reactions are at equilibrium, because the process at high temperature process 1600 degrees centigrade. So, you can assume a equilibrium, okay, at least at the reaction interface, that is those are in equilibrium. So, what is the rate controlling step? Rate controlling step is basically the transfer of impurities from metal bulk to the interface, or transfer of FeO from the slag bulk to the slag interface. Okay. So, if you do that is a mass transfer control, in that case you can write several mass balance equation for different impurities in the hot metal and oxides into the slag. Okay. So, those some of the equations that I am writing it. So, I have written it because otherwise it will take time. Just now I have written, and yeah, this is the phenomenological model. So, you can calculate, for example, d in SI dt, that means the rate of change of silicon into the hot metal, that can be given by, that is the mass transfer coefficient for silicon into interfacial area divided by the volume of the metal phase into, this is called volumetric mass transfer coefficient or volumetric rate constant, you can say, because it has a unit km. Km has a unit of centimeter per second, A centimeter square and V centimeter cube. So, this unit has a unit of per second. Okay. So, Km is the mass transfer coefficient. Mass transfer coefficient, as you know, it basically gives you the conductance through the concentration boundary layer on the metal side, right. And into, that is this rate constant into first order rate constant into, it is this thing N SIM, that is the silicon concentration into the bulk minus of silicon concentration at the interface, as the moles of silicon into the bulk, moles of silicon in the interface concentration. Okay. So, that is the way you can define the flux multiplied by the area, that is the thing. So, you know at heterogeneous interface we can always define the flux K into delta C. So, that I have done. Okay. So, If you do that, then you can get, that is the rate of silicon consumption. I am assuming rate of silicon consumption is directly proportional, that is the rate of silicon consumption from the bath is controlled by transfer of silicon from the bulk to the interface, that is defined like this mathematically. Similarly, that is the manganese for rate of change of manganese into the hot metal can be given by this equation, rate of phosphorus can be given by this, carbon can be given by this, simple like that. Now, interface concentration, as I said, there is the at the interface you can assume equilibrium that is all the chemical reaction are at equilibrium at high temperature, because since the process is taking place at 1600 degrees centigrade. So, you can the activation energy will be quite less and chemical reaction will be fast enough. Only mass transfer can be rate controlling, that is the justification of this assumption. And this equilibrium interface concentration or the equilibrium concentration you can calculate simply from this equilibrium correlationship. So, silicon for example, oxidation you can define like this, Fe in the slag will react with the silicon into the metal giving rise to SiO2 that will join the slag and the iron it will form. So, KSI equilibrium constant you can write it as, that is the activity of SiO2 by activity of FeO and the activity of silicon, and activity of silicon is written in terms of 100% standard state, that is why it is written H into Si. I think you know all this thing and it is not possible. And then mole fraction of silicon you can write basically, that is the mole fraction of silicon you can write N of Si equilibrium is given by this thing. Basically, yeah, that is the thing, this is the relationship basically, this is you are getting basically x of this. And I think here it is a little mistake is there. Okay. So, this is basically what we are getting is why it is not working. Oh, it is in the PDF, that is why. Anyway, so NSI and Xi, there is the mole and this is the mole fraction of Xi into total moles of impurities into the metal. If you know, you can correlate this thing, that is the mole of Si to the mole fraction of Si, and you can get the mole fraction from this formula. Okay. So, this is the way you can get it. And this is for the impurities into the hot metal, that is the mass balance equation for the impurities into the hot metal. And then similarly, I have written similarly FeO, that is the rate of consumption of FeO into the slag phase you can define, because how much the FeO will be consumed, because 1 mole of silicon consume basically 2 mole of FeO, because as you have seen, because it forms the SiO2. Actually, here it is wrong, basically it will be 2 FeO plus Si is equal to SiO2 plus twice Fe, right. So, in this correction you can make. So, in FeO basically 1 mole of FeO will be consumed, there is the 1 mole of silicon consume 2 moles of FeO. So, if you know the silicon rate, that is the FeO consumption will be 2 times of silicon rate. So, once you know the impurity consumption rate, you can calculate what is the rate at which the FeO will be consumed. That is what I have written, this is by mass balance equation. So, then initial value of FeO you can calculate from here, that is the what is the FeO into the slag phase, that you can calculate from this. So, if you know the partial pressure of oxygen, you know the dissolved oxygen, and then FeO Fe relation, from this relation you can calculate, that is the mole fraction of FeO in terms of dissolved oxygen. So, in terms of partial pressure of oxygen. Okay. And so, and this partial pressure of oxygen basically at the bath characterize what is your volume flow rate of oxygen and also what is the length height, all these things will influence the what is the partial pressure of oxygen on the bath. So, you can correlate, there is the FeO concentration into the slag with the your length height as well as volumetric flow rate of oxygen. Even the interfacial area that we have used in the previous page, there is the interfacial area, that means in the refining of into the LD furnace is that your hot metal is ejected into the slag phase, right, or the I will say foam, that is the gas slag foam. Hot metal is ejected in the gas slag foam and it forms an emulsion, and then at the slag metal interface the reaction takes place. So, there is the tremendous increase in surface area because metal droplet moves into the slag phase, okay, or the slag foam, and as a result your interfacial increases. But how to calculate the interfacial area, that will depends on the Reynolds number, turbulence of the bath. I am just characterizing by Reynolds number, because more the turbulence or the more the impact on the bath, more will be the your that is the your droplet generation, because more the pressure, more will be the FO, and then CO can form homogeneously and it can create a tremendous pressure, and then that basically ejects the metal droplet, fine droplet into the slag phase and with tremendous surface area. Basically it will depend on surface area, you have to find out what is the correlation you will use, but it will depend on the Reynolds number. So, then other mass balance equations are, for example, CO, calcium oxide. For example, you know it forms the tricalcium phosphate, tricalcium silicate, all these things. So, rate of consumption of calcium oxide or the rate of that is the consumption of calcium oxide in the slag phase, you can define as minus of 3 rate of phosphorus transfer as well as rate of silicon transfer. So, this is also simply mass balance equation, and then P2O5, how it will evolve the P2O5 into the slag, it will depend on the rate of phosphorus consumption from the hot metal. Similarly, rate of generation of MnO into the slag phase will depends on directly on the rate of depletion of manganese in the hot metal. And finally, these are all the mass balance equation for the impurities as well as the oxide phase into the slag. Similarly, you can make an heat balance equation too. So, we are considering that is inside the hot metal there is no gradient, that is thing, it is continuously stirred. So, no gradient I am considering, only temperature is evolving with time. So, in that case you can write rho Cp dt dt, where T is the temperature of the hot metal, and this will depend on two parameters. One is called the heat effects of chemical reaction and mostly exothermic. Okay. So, it will basically, this is the source of energy. So, Ri and delta Hi minus this is the scrap dissolution rate into the latent heat of the scrap. Okay. So, scrap dissolution rate also you can consider heat transfer control, then that dissolution rate will be simply equal to H into A into delta T, which H is the heat transfer coefficient at the metal's liquid scrap interface, okay, in the boundary layer, thermal boundary layer, that is the heat transfer coefficient, and area is that interfacial area, and delta T is the temperature difference. And also that is the way you can define the scrap dissolution rate, dm scrap by dt into the latent heat of scrap. So, this is the amount of heat that is absorbed by the scrap dissolution and the heat is generating. And also you more add one more term, right, lot of heat will be lost from the surface, that also can be defined by H into A into delta T, that is the delta T is the liquid temperature minus the your ambient temperature, H is the heat transfer coefficient at the refractory air interface. So, that way you can also, you have to add another term, that is also heat is being lost. So, if you consider this thing, then you can know the evolution of temperature, right. Now, finally, solving the above ODEs, all these ODE if you solve, then you will get the evolution of the impurities as well as oxide as well as temperature in the bath, okay, bath and the slag phase. So, now what I am telling is that, so you now train an ANN model with this phenomenological model, then when the ANN is trained, so it will predict will be based on physics, okay, and ANN has the capacity of the backward modeling. So, now you can use that trained ANN for inverse modeling or the backward modeling. So, you can say for a particular carbon concentration and temperature, desired carbon concentration and temperature at the end point, what should be my operating parameter at any time. You can use this model dynamically also. Okay, so that is how it is ascertained. So, if you want to ascertain the tapping condition, that you have to attain a desired carbon concentration and the temperature at the tapping stream. Okay. So, for that you have to use model to back predict what will be your operating parameters. So, this is the just I am telling that is the mass balance equation you can use, and you can train it with the neural network, and then you can back predict. So, this is I think one approach it can be. Okay, now second question was the irregularities in the blast furnace. Why that is explain various irregularities in the blast furnace, their mechanism of arising. Now, irregularities of the blast furnace, lecture 11 I think, yeah. I talked about the aerodynamics in the blast furnace. If you remember, this lecture you have heard about, okay, importance of aerodynamics, okay, this thing. There are basically two types of irregularities that happen into the blast furnace. One is in the dry zone, one is in the wet zone. In the dry zone, the major irregularities is called the channeling. Channeling means what? That is when the gas passes through some selected channels, okay, because the gas, the permeability of the solid bed is not uniform. Some places it is very porous, in some places it is totally impermeable to the gas. So, gas cannot pass through those regions. So, when this situation arises, that is certain selected channel only offers the least resistance part, then the gas preferably flow through those regions and preferably flow through those regions. Okay. So, that is called a channeling. That situation is called channeling. Then channeling, what is the problem? Problem is that you are not utilizing your gas. Since the gas cannot interact with most of the solid, then what happens? Your gas remain unutilized with respect to both its chemical potential as well as thermal potential. The gas has two purposes. One is it has to supply the heat to the solid such that it get heated up, and another function is that that is the reaction. So, through the reaction, that is your mass transfer take place. Basically, CO moves in, it reduces and the CO2 comes out. Okay. So, that is the thing. So, thermal and chemical potential of gas, if you want to utilize effectively, in that case you have to have a uniformly permeable bed, okay, such that the gas can pass through across the cross section and it can interact with the solid, okay, most of the solid, such that you can effectively utilize the gas potential. But in case of the channeling, when the gases are passes through some selected channel, so the most of the solid remains deprived of interaction with the gas. So, they do not get reduced, only the selected channel, some amount of the solid get reduced, and also heat transfer also take place locally. So, as a result, what happens? The gas comes out with a very high temperature, with a very high CO concentration, unutilized CO concentration, and the efficiency of the furnace become very low. So, this is one of the irregularities that is called the channeling. Another irregularities in the blast furnace is, I am just telling and then I will come to this. Another irregularities in the blast furnace is your that is called the flooding, and flooding take place in the lower part of the furnace in the wet zone. In that zone also, you know, that is the liquid is coming down in the wet zone and gas is moving up. Okay. So, in flooding situation happens basically when the resistance in the gas passage, when the resistance to the gas passage increases, okay, as you know, that is in the lower part of the furnace, you have only cohesive zone and the coke slit through which only the gas can pass through. So, if the resistance for the gas passage increases, in that case what happens? That is the gas can physically push the liquid upward. So, if it pushes the liquid upward, then liquid can move into the lower temperature solid region and they can solidify. So, if they solidify, they will form an impermeable arc, solidified liquid iron, there is arc, and as a result the gas will not be able to flow at all in the upper part of the furnace. Oh, that situation is called, that is the furnace is refuses to take the air, that is called, the situation is called the hanging. So, then the hanging take place. Okay. So, this is the two conditions Okay, so this is in the wet zone. This is the basically if the permeability, there is the gas passes through the wet zone, resistance to the gas passes through the wet zone increases significantly, then gas pushes the liquid upward, they solidify in the upper part, and then gas cannot move at all. So this is the condition called hanging. Before that, it is called the flooding. Flooding means when the liquid is pushes in the upper region and then it floods the lower temperature regions called the flooding, and finally significantly leads to the hanging. And in the upper part, it is the channeling. And both these problems appear because of aerodynamics. We do not look into the aerodynamics properly. Why the channeling take place in the upper part of the furnace? This is the two problem I am telling, two irregularities. You first said, please explain the various irregularities. I think I have explained properly. That is the two irregularities exist. One is the channeling, flooding. Channeling take place in the upper part of the furnace when the gas passes through some selected channels, and and as a result your thermal chemical potential of the gas is not utilized properly. As a result, efficiency of the furnace decreases. And also what happens if channeling take place for some time, then the solid at a much lower temperature can descend to the lower temperature, that is in the wet zone, and as a result your thermal imbalance will be there, and everything can freeze at the bottom. Thing is that because the solid in the upper part is not getting preheated to a significant extent. So, it is a cold solid material will come down in the lower part of the furnace and it can freeze everything, and it will be total catastrophe. So, thing is the channeling should not exist for a long time, because a majority of the solid do not get divided of preheating reduction, you just left it out. Okay. So, no, not sufficient preheating also take place. Okay. So, this is one problem of channeling, and lower part, as I said, there is the gas passes through only to the coke slit in the cohesive zone, and if the resistance increases significantly, then liquid is pushed up, it floods the upper region and forms a solid arc and does not allow the gas to pass through. That condition is called a hanging, and and hanging condition you can understand is the gas is not being able to pass through, how it will produce. So, this is the two major irregularities that take place, and aerodynamics plays a important role in this thing. Okay. So, remedial action, that is the what is the mechanism, how does it take place. So, mechanism if I say, then okay, now I can go to the slide. Not this one. Okay. Yes. Yeah. Okay. So, what is the time? 9 time. So, thing is yeah, I have done, I think, here. One situation I have given example where I think not this slide. Okay. Yeah. So, this is I pictorially tried to show what is the mechanism of channeling. You can see that here I have just in the across the cross section I have tried to show the permeable region. Obviously, you can see here the fine concentration is less near the center, and also near the periphery also fine concentration is less, and these are more permeable region. Anyway, at certain time center and periphery it is the more permeable region, and the gas is also flowing to the central region, but it is not flowing to a very high extent. It is comparatively less flow rate, because here some resistance are there. Okay, because more of the fines are accumulated into the central region because of, you can see it is an M profile In M profile, the charging is done on the middle, that is this little area from the wall. So, this region the charging has been done. So, as a result the fines because fines, as you know, because of low angle, very high steep angle of repose, they cannot move far away. Where they are charged, basically they try to sit in that location. Since the charging had been taking place here, so fines are accumulated in this middle region. So, away from it, the fines are less in the center and the periphery, and also in the center and periphery coke percentage is also high. As a result, you are more permeable, right, and fines is less. And the middle region I showed you, that is, it is less permeable, but gas is passing through it. Now, what happens if I want to produce more, that is, if I want to increase the productivity, then what I have to do? I have to increase the blast rate. Obviously, if you want to produce more, you have to burn more carbon per unit time, then only you can melt more iron per unit time. Productivity means higher means what? You want to melt more iron per unit time. So, as a result, you have to melt more carbon per unit time, that is the coke throughput, that is called, you have to increase, and as a result you have to give more blast, there is a more oxygen you have to supply to burn the extra carbon per unit time. So, blast rate has to increase. Blast rate means per unit time, what is the volume of the air blast that you are pushing, that has to increase. So, if you increase that, then what happens? As the velocity, the linear velocity through the blast furnace will increase, and as the velocity increases, obviously the frictional resistance also increases, or the you can say frictional drag, okay. Frictional dissipation also increases as the velocity increases. So, pressure drop also increases. So, as the gas velocity increases, the pressure drop will increase. Pressure drop, I know that the top pressure minus the bottom pressure, okay. This pressure drop will increase because you have lot of frictional dissipation, so energy loss. So, this pressure drop or the resistance to the flow increases basically. If you increase the gas velocity, resistance to the flow increases. So, what will happen? Because the pressure drop increases, you can, I have shown you that thing, this is the velocity profile, and then I have shown you a typically schematically a pressure drop like this. So, pressure drop is maximum at this central region, you can find at this region the pressure drop is maximum. Now, if you increase the gas velocity further, that is the blast rate or the linear velocity of the gas increases into the blast furnace, then this pressure drop will further increase. So, this pressure drop now will go further increase. If you increase this pressure drop further, then what happens? A situation may arise when this fine will get fluidized, because the pressure drop is increasing higher and higher, and then the condition of incipient fluidization can take place. Then this, and if you further increase it, the that is what is that? That is the fluid particle will be completely fluidized. So, if it is fluidized, small particle, I am talking about this fines will get fluidized and it will move up, just like I have shown you here, that is the fine particle is moved up because it fluidized, but it cannot move very high, na? It can go up and then again come down, because up also there are a lot of resistance because of all burdens are there. So, they will be hit up and then again they will come down. So, these fines after get fluidized, they again return back and deposit here. So, this region, and what happens when this fines moves up, then you can see this particle, between this particle some voids are created, because the fines were sitting there. As they get fluidized, those voids are created. As a result, the surrounding particle may consolidate, they can move each other, they can further consolidate. So, consolidation of the, so this consolidation, that is the particles will come out, because of void creation the particle will come closer, more consolidation will take place, and then the fine particles which moves up again will return back and sit on the same place. So, as a result, this region become more impermeable, this region become more impermeable because of, it is called the ore shift. So, ore shift, and then your fines again deposit in the same location, because after fluidization they will again come back. So, they will again come back and then sit, and as a result what happens? So, in this case, so this is the error. This basically I showed you, there is the pressure drop suddenly picked up, and then when fluidization the pressure drop again may come down, right, this after that. But and then basically what happens in this region, it becomes a further impermeable. it is to become totally impermeable because of work shift as well as fine deposition in the same location. So, it does not remain as permeable as before. So, it become very impermeable, and in that case gas will find a path through a small central region and the periphery region maybe. So, that is the two channel, perfect channel can be created in the center and the periphery, and the gas will pass through that thing. So, thing is that this localized fluidization sometimes make that region further impermeable because of work shift as well as fine deposition over it. So, as a result it becomes highly impermeable and the gas only pass through certain selected region. So, this can be one of the mechanism. Okay, so, mechanism is basically local fluidization. You do not allow any time any local fluidization anywhere, because if it take place, then because of work shift and again final deposition of the fines, that regions will be further impermeable. So, what is the remedial action is that before it can happen, because you have lot of underburden probes nowadays in axial and radial direction. So, you can easily measure you can easily map the what is the local pressure drop. If you find in some place the pressure drop is increasing, in that case you can change the burden distribution, and that place you can charge some amount of coke in that place, but now we have the bell-less charging. So, wherever you want the permeable material you can charge. So, coke is more permeable. So, if some places is going to be very impervious, so what you do, you can charge some amount of coke in that location such that the liquefaction slowly becomes permeable. So, thing is that based on the underburden probes, based on the mapping of the pressure, okay, local pressure drop, you can always monitor it. If pressure drop is increasing someplace, you can make it permeable by charging some coke in that location, and that is the way, such that that is the way you can take some corrective actions. Okay. And that is the way. And also another corrective action in the pressure drop, that is the most important thing, is the height of pressure. That is another thing, that is that you can do. If you find this localized pressure is increasing, you can increase the height of pressure. What is the height of pressure? That is the pressure at the top you can increase. If you increase the pressure at the top, what will happen? Bottom pressure remaining constant. So, if you increase the top pressure, the overall pressure drop will decrease. If the pressure drop, you can decrease that way also. So, you can increase the height of pressure such that the pressure drop in the furnace decreases. Overall pressure drop will decrease, the local pressure drop also decreases. So, that is the way. So, I have shown you that is the height of pressure, some calculations are there, that is the Argon equation you can write like this, and then that Argon equation keeping other thing constant, if the pressure only changing and the velocity is changing, other remaining constant, you can write this way dph dt, and then you can have this correlation, that is the P average into delta P is equal to K prime in W. So, you can see the product of average pressure and the pressure drop is equal to directly proportional to the your linear velocity to the power n exponent. N is called the exponent, and this n value is around 1.75 in the blast furnace. So, you can is easily used, and so that you can calculate. Suppose you want to increase the blast rate by 30%, 40%, whatever it may be. But if you do not want to increase the pressure drop, then what is the height of pressure you need? That you can simply calculate using this formula. So, this is that is the height of pressure is obviously a remedy. If you increase the blast rate, increase the height of pressure such that the pressure drop remain constant, it does not change. So, that way you can avoid the channeling. Okay. So, this is about the channeling. Now, I can talk about you, that is the flooding. Flooding also we have discussed. Okay, let me see in between some question has come. Okay. Okay, I will just and then can you feed the sinter plate? I will come to that thing. Okay. Let us tell the flooding and then I am coming back to those questions. Okay. Okay, okay, I have to go revise it. Okay. Okay, mechanism of flooding, that I was I have to discuss why the flooding that take place. You can see in the solid bed, you have a solid bed and you are pouring some liquid from the top as shown in the figure. Okay, you are pouring some of the liquid from the top and gas from the bottom. Then what will happen, and if you increase the gas velocity, progressively you are increasing the bottom gas velocity, then what will happen, there is all the liquid that you are pouring from the top won't be able to come down, because partially certain fraction of the liquid will start residing into the solid bed, that is called the holding. And holding take place as at a certain gas velocity and certain liquid velocity, there will be no holding in the liquid. Okay? When the gas can safely pass through it and liquid is coming down is fine. But if you go on increasing the gas velocity, a situation may arise, then your what will happen, if you continuously go on increasing the gas velocity, then a certain amount of the liquid is start holding into the solid bed. Okay, because that much of a fraction of the liquid will remain into the solid bed, they cannot come down. So, if you go on increasing the gas velocity, then this amount, there is the fraction of the liquid into the solid bed will go on increasing, that is the hold up will increase. And if you further increase the gas velocity, then you will find the hold up, liquid hold up will become 100%, that is the 100% of the liquid is not being able to come down at certain gas velocity, that is 100% hold up. And if you further increase the gas velocity, what happens, it will physically push the liquid in the upward. So, that is called the condition of flooding. So, in the blast furnace, I have drawn this nice picture. You can see this is the cohesive zone and this is the coke slit. White regions are the coke slit and the red regions are the fused mass of iron and slag. So, you can see the gas is coming and passing through the coke slit and moving up. So, only gas has the passage only this region, that is the coke slit through which the gas can pass in the finally the cohesive zone. So, now if the gas velocity increases, what happens is that this coke slit, that is so because of resistance increases, that is this coke slit also partially get filled up with the liquid, because your resistance is increasing, because gas is moving up. Okay? So, liquid is not being able to come down properly. So, part of the liquid is start holding on the coke slit. You can see this is the holding is taking place into the coke slit. So, gas passage basically decreasing, that is the through which the gas passage decreases, that is decreases, gas can pass, okay, that decreases. And with increase in the gas velocity, what happens, a situation may arise, then whole coke slit will be filled up by the liquid. So, then the gas do not have any path to go up. Okay? So, in that case what the gas will do, gas will basically push this liquid upward and then it will move up. So, that is happening, that situation take place, that is called the flooding. So, when this liquid, when the liquid moves up in the region, then in the and then the low temperature region, this liquid can solidify and cause a condition of hanging. Okay. So, this hanging take place. So, what is the remedial action? That is again the remedial action will be similar, that is you decrease the pressure drop. If you increase the height of pressure, that will also act here, because the pressure drop will decrease, because you are pushing, that is the high pressure from the top is high. So, both pressure drop will be there, or another lot of other remedial action is there. You can use that is the bigger coke, such that a specific surface area is more in the lower part of the furnace. So, that you have to see, if some flooding tendency is taking place, you use a little bigger coke, such that when they come down in the wet zone, the coke size is significantly higher, that can offer a higher specific that is the specific surface area become low. Okay. So, that is the way it can be done, and there are obviously you can play with the some of the parameters you do not have handle, that is the density or the viscosity of the slag. Also the viscosity of the slag and the weightability of the slag, on these two parameters you can control it to some extent, but in that case slag composition you have to change properly. Okay. So, these are that is the flooding limit, some correlations are given here, that is the F square K, where F is called the flooding factor and K is called the fluid ratio. So, this is the way you can do that. And you can see when the F squared dot K that is greater than equal to 0.001, when it is greater than that, then the flooding take place. So, this is the line basically, this is the line, and all the data you can find below it. If it is below it, that flooding will not take place. If the data goes below above it, then the flooding will take place. So, accordingly you F and K you can control in such a way such that all the data remains beyond this line. This line is nothing but that is this line, log F of, log F is equal to this line. So, this is the straight line basically. If you plot the flooding factor in a log scale and fluid ratio into the log scale also, then it will become a straight line and all the data. So, you have to control this F and K in such a way such that all the data remains below this line, then you can avoid the flooding. And this flooding factor and fluid ratio also depends on the physical parameter this way. Okay. So, where nu is basically the velocity, linear velocity is very important term. So, you try to reduce the linear velocity. So, if you use the top pressure, high top pressure, even if you increase the blast rate, if the pressure drop does not increase, the V will not increase. So, that way you can control the flooding. That I am telling, high top pressure you can use to reduce the, that is the velocity, okay, linear velocity through the blast furnace. And then as I said, your voidage, obviously the gas voidage should be as high as possible, then the flooding factor will be low. Density of the liquid, if it is high, then basically the flooding factor is low, because if the you cannot have, don't have any control, that is composition. If you change a little bit, that is the density of the slag, basically you cannot control too much. But and then Fs is basically the specific surface area of the coke. So, if it increases, that is, then the flooding will become more. There is a specific surface area should be as low as possible. That's why I am telling the bigger size of coke you must use, such that when they come down into the wet zone, their size is sufficiently big such that specific surface area of the coke is less. Because the higher the specific surface area of the coke, because the coke will be weighted. If the cokes are very fine size, they will be easily weighted by the liquid, right. If it is bigger, then weighting will be less. That is the low surface area. Higher the surface area, higher will be the weighting. And also the slag weighting, that is, if you can make a composition of the slag in such a way, is non-weightability increases, that is better. If they cannot weight the coke, then the gas will find the passage. So, that is another thing. So, this way, that is the L is the superficial liquid, that is the liquid velocity, and this is the gas velocity. L and G are there. So, this factor basically, if you can control this, you go through this note, if you can control this, that is finally your aim is F square K should be less than that line. That is the all the data should be below this line. If you plot it, data should be below this line, and for that you can control the physical properties of the slag, like density or the viscosity or the weightability of the slag, and then you can control the velocity by high top pressure, you can control. And the liquid velocity, the volume of the liquid, obviously slag volume, if you can reduce it is better. Higher the slag volume, okay, higher will be the K, and the flooding tendency will be less, more will be high. So, those things are there. Okay. So, this is the thing basically, as far as, let us see what are the question you have asked. Acha, Suman Datto has one question, I think it is from the first one. First question, that is how the interfacial area is dependent on Reynolds number, please explain. So, how the interfacial area, right, that is the interfacial area basically when the liquid droplets is ejected into the slag phase, okay, it depends on the liquid turbulence to some extent, okay, because higher the liquid turbulence, which higher will be the ejection. Basically, why I am telling, I am just telling in a very loudly, that is the Reynolds number, to tell what is the turbulence of the liquid. Okay. If the turbulence is more, basically you are more of ejection, that is the finer will be the metal droplet into the slag phase. And turbulence in other way, it depends on, that is the how much energy that is coming from your oxygen jet into the, but what is the impact, okay, what is the impact on it. So, that I am telling, I am just writing there is the, that is based on the Reynolds number, there is the turbulence into the liquid, okay, and it will depend on the, also on the impact of the oxygen jet on that thing. Anyway, that you have to calculate, that is the interfacial area basically will be calculated from how many droplets are being created per unit time. It is better be I am just written the Reynolds number, but it better be related with the specific energy input, okay, because how much energy you are giving, based on that, that is the droplets will be created, because droplets means you are creating new surface, or you can see that is the higher is the droplet, higher is the energy into the surface. So, how much energy you are putting into the liquid still from that. I have not given exactly how you calculate the droplet size, that you have to do that thing, that you have to see literature, how you can, people can calculate the droplets and number of droplets with the impact of oxygen. There is the energy input, you can better correlate with the energy input, okay, energy input and the droplet size. Because finally, when the fine droplets are moving into the slag phase, you can calculate, and that is the energy is increasing, because you are creating new surface, and each surface involves certain amount of energy with it, surface energy. So, the total energy that you are giving, if you assume that is the all the energy goes into creating those droplets, then you know what is the total energy of the droplets, okay. And then if you assume some droplet size, then you can calculate the number of droplets. Okay, so that is the way, or you can assume number of droplets, you can calculate what is the total surface area. So, that is the way you can calculate. I have just told you that is a function of Reynolds number, okay, but to show that is the, obviously the turbulence has a role to play that way. But exactly I have not shown how you will calculate it, but I think it is better you can correlate the droplet size with the energy input. You can go through some literature and get it. Can we feed sinter and pellets simultaneously as iron agglomerate into blast furnace? Oh, sinter and pellets. If the question, if I understand, can we feed sinter and pellets simultaneously as iron agglomerate into blast furnace? I don't know getting, or we have to use only one of the agglomerate in blast furnace. Oh, it is the question to the blast furnace. Okay, okay. I have just correlated with it. Yeah, okay. Can we feed sinter and pellets simultaneously? Yes, yes, you can simultaneously charge sinter and pellet in the blast furnace. What is the wrong in it? You can do that, and that is absolutely no problem, and not only one, because you see these are the better than the lump ore, because pellets are not usually charged because it is costly, that is why, and otherwise pellets is a very good agglomerate. It has very good specific surface area, reactivity, everything. So, it depends on the economics. More the pellets, better will run the blast furnace. If you 100% pellet blast furnace, it will be better. But pellets are also some problems are there, like swelling properties. Some of the pellets shows catastrophic swelling, especially if alkaline metals are there, sodium, calcium. So, then otherwise you will behave pellets. If it is 100%, it is better than blast furnace. You can do that. But always it is better to mix some sinter and pellet, because pellet, if those have swelling tendency, because swelling tendency cannot be tolerated into the blast furnace, because they will form the, what will form? They will form the, what is that called, fines. Okay. So, but absolutely you can use both. You can always mixture of sinter and pellets into the blast furnace. Both are the very good burden for the blast furnace, and even pellets are better than sinter as far as the reactivity and the strength of the strength is concerned. Okay. Okay. Then Anup Mandal, please describe the effect of slag viscosity on flooding effect. Just now I showed you slag viscosity. If you increase the slag viscosity, your flooding factor increases. Slag viscous means what will happen? It won't be able to come down very easily, because it is viscous means it has a lot of drag. So, at the heterogeneous interface it will have a lot of drag. So, slag won't be able to come easily if the slag is highly viscous. In that case, so think is that your flooding will be little more, F will increase. Okay. So, that is the thing. Can we alloying with elements copper, manganese, silicon to the base metal iron in vacuum induction melting? I am not getting this question. Can we alloying with elements, okay, copper, manganese, silicon to the base metal iron in vacuum induction melting, okay, through charge store? But you say it that these elements will distill off under the vacuum. Yeah, thing is that manganese will distill off, and copper I have not said, I have said only the manganese. So, thing is that manganese will distill off greater than 1% as I said, because its vapor pressure is high. So, you cannot alloy manganese under vacuum, it is difficult to do that. But silicons also form in presence of sulfur SiS gas, then also it is a problem. But copper you can do it, copper do not have that much of vapor pressure. But manganese you cannot do it, manganese has the very high vapor pressure, and silicon in presence of sulfur also can form SiS gas, okay, that also it can do that. Okay, the increasing the Arup Kumar Mandal, okay, increasing the size of coke will increase the bed permeability. Is it the another reason of decreasing flooding? Actually, whether the size is big or big or small, basically bed permeability is higher with the coke. Okay. So, bed permeability will be there, that is not the question here. So, thing is that when the size is more, specific surface area is less, basically is less, right. When it is bigger, specific surface. If the specific surface area is less, the slag will not be able to weight the surface. So, the gas can utilize those passage. Okay, that is the thing. That is the major thing. Okay, it is not that size with the permeability too much. Okay, obviously. Bigger side bed, if you make a bed, then the force will be bigger like that, but that is the thing. Okay. Okay, so this is the thing, that is the bigger the size, weightability is less, that is the slag won't be able to, that is the, what is that, the minimum the surface area, the slag weightability will be less. So, better you also work with the weightability of the slag also, if make the composition in such a way such that the slag does not weight it, then it is better. And even if you make it bigger size coke, then also surface area decreases, the weightability decreases, and that is the what is the slag won't be able to weight that much, because there is less surface area. Okay, I find there is no question anymore. Okay, so if you have any further question, one question I can take up, you can just type and send it to me just now. Okay, if you don't have question, I close it here. Thank you very much. We will again meet for another live session later on, and that time I will request you send as many questions as possible. Okay, fine. Bye. Thank you.